In this video, we're going to talk about optimization. And in particular, we're going to be looking at the first example of an optimization type of a problem. So in optimization, we look at a particular scenario. We're going to find a function related to that, and then we want to optimize that function. What does that mean? That means we want to find a maximum or a minimum of that particular function. And we will see how to do that by working through this example. So let's go ahead and get started with that. So let's suppose we have an open top box that is to be made by cutting a small congruent squares from corners of a 12 by 12 inch sheet of tin and then bending up the sides. We want to know how large should the squares be to make the volume of the box as large as possible. So let's go ahead and draw a picture to see what that means. This should be your first thing that you do for each of these problems, will be to draw a picture if appropriate, but that will be appropriate most of the time. So we have a 12 by 12 sheet of tin here. And we're going to be cutting out small congruent squares from the corner. So we're going to be cutting out pieces here and here. How large are those pieces? We don't know yet. Maybe we should call them X. And then what you're going to do is you will fold up these sides after you cut this away. After you cut those away, you'll fold up these sides along these solid lines here to make a box. So that's what we're trying to do. Now, to be able to optimize this question, we want to again recognize, well, what are we trying to optimize, right? So it says how large should the squares be to make the volume of the box as large as possible. In other words, what is the value of X here to maximize the volume? So we can do this by finding a volume equation. So let's write down our volume equation. Well, our volume is length times width times height. Well, our length is a total of 12 minus the piece here and minus the piece here. Each of those distances are X, so this is 12 minus 2X. The width is the same thing. It's going to be 12 minus 2X. And when you fold up these pieces, the height of the box will just be the value X. So this right here gives you the volume of the box in terms of the variable X. So what is this? Well, let's go ahead and multiply everything out in order to simplify our derivative. Oh. 48x squared plus 4x cubed. All right, so we get 144x minus 48x squared plus 4x cubed as our formula for the volume of the box. Also notice that the x value must range between 0 and 6. If X is 0, that means we're not cutting out anything here out of the board. So we can't even actually fold anything up. And so you get a volume of 0. If we have a value of 6 here, that would make the squares 6 by 6, which means we would be cutting out the entire board or the entire piece of tin there. And so we'd again get a volume of 0 there. All right, so we have this interval, in which case X must be between 0 and 6. So essentially we have a closed interval problem. We're trying to find a maximum value on a closed interval from X equals 0 to 6. How do we do that? Well, we find our derivative. And then we set that equal to 0 to find our critical values. So we can factor out a 12 here, and we get 12 minus 8x plus x squared is equal to 12 times x minus 6 times x minus 2. Except 6 is not inside our interval. It is at the endpoint here. But we're already going to take care of that. So we don't need that value of 6. We're already going to plug in that as an endpoint anyways. So, in fact, let's do that. We need v of 0. We need to plug in that endpoint. V of 0 is 0. We also need to plug in the endpoint 6, which is also clearly 0. And then we need to plug in our critical point, so v of 2. Well, if we do that, right, we're plugging into the original equation here. So 12 minus 2 times 2 times 12 minus 2 times 2 times 2. Multiply all this together, we get 8 times 2, which is 64 times 2, which is 128. And that would be cubic inches. And this is larger than, of course, the zeros that we got over here. So the max volume is 128 cubic inches and occurs when x equals 2. So we cut out a 2 by 2 square in each of the 4 corners and then fold the box up from there. And that completes this first example on optimization. Stay tuned for the next video to do the second example.